So hey everybody, welcome to ARE Live. I'm Mark Tier, the founder of Black Spectacles, and today I'm sitting here with Mike Newman, who's going to talk about the structural systems mock exam that we issued. Mike's going to review different types of questions and some of the strategies for how to answer those questions. We were just talking about it earlier, and there's actually quite a few different types of questions, from sort of structural detailing questions to questions about code, to maybe the more kind of common and obvious questions about loads and so on. So Mike's going to get into those different types of questions and help you kind of with some strategies for how to answer them. But before we get going here, if you'd like to attend our next ARE Live broadcast, where we're going to feature recently licensed architects and their strategies for passing the ARE, let's see here, you can visit blackspectacles.com/podcast. And you can see here where the Register Now button is. You can go ahead and register for that. And just like all of our other ARE Live broadcasts, you'll be able to ask questions to the group of folks who pass the ARE, as well as Mike. And if you don't know Mike, he's an assistant adjunct professor at the School of the Art Institute of Chicago. He's also the founder of Shed Studio, and he's the instructor for Black Spectacles' online AIA ARE Prep curriculum. If you haven't already checked out our AIA ARE Prep curriculum, head over to blackspectacles.com to watch any of the free tutorials from the courses. And today we have a special Black Spectacles promo code to share, so make sure you stick around until the end of today's episode. But first, let me go ahead and hand it over to Mike.
Thanks, Mark. Yes, as you say, there are many possible questions that could show up on this exam, like all of the exams. And that range makes it a little daunting and complicated to study for. But hopefully what we're going to do today is just do a quick little breeze across the top of a few different of these topics and allow us to sort of see the kind of range and the kind of types of questions. And I'll talk a little bit about the ways that NCARB writes their questions and the sort of type of questions that come up on this, like why they write them the way they do, and kind of what the point of the questions are, so that we can really sort of jump into it. One of the things you mentioned, Mark, was the code questions that show up, so not just detailing, not just loads, but also a whole range of other possibilities, including code questions. That's one that I was a little surprised by recently as I was going through a lot of the new documentation from NCARB. In the recent materials that they've sent out, they now focus much more on code questions. Not that it's a huge number of them, but that just more than they had been focusing before. So things about IBC and like load reductions for wind loads and those kinds of topics. So that's something that we're not going to talk about today really, but I would recommend that probably doesn't show up as much on a lot of the guidebooks as it will soon, because it's clearly a big focus on the NCARB front. So given that, I think we should just jump right in. All right, so the little mini mock exam that we sent out starts with a fairly simple, straightforward statics question. And the question is, number one, neglecting the weight of the beam, what are the values for both of the reactions of R1 and R2? So the key first thing to remember here, just remembering back to your early days, is the idea that the sum of the forces equals 0. So the sum of the horizontal forces equals 0, and the sum of the vertical forces equals 0, and most importantly, probably, is that the sum of the moments equals 0. Remember, a moment is a force times a diagram. Remembering that, we don't really have, on this particular example, any horizontal forces, so we're going to actually not worry about that one right now. What we will focus on, though, is on the vertical and the moments. All right, once Mark's out of my way here. All right. First thing we need to figure out is what are our loads going vertically, in this sense, down, so that we can then figure out what our loads are going vertically up. And the best way that we're going to do that is by actually figuring out what one of those loads is by doing moments around one of the reaction points. We could actually do moments around either of them. The main thing is we have to get rid of one of them. And the reason that we can get rid of one is because if moment is a force times a distance, if the distance is 0, it just goes away. And so that allows us to have only one variable that we don't know. So if we do it, say, around this point at R2, that means the only one that will be left will be R1, and so we can do the calculation very simply and easily. So if the sum of the moments, so have to equal to 0 for it to be in equilibrium, i.e. it's not going to fly away, float off, or bury itself into the ground, so it's in equilibrium we're assuming. So then we start to think about, all right, the sum of the moments around this point. The moments again are a force times a distance. So here's a force, the 2k. So the distance is 5 feet. I'm going to call that force, because it's going down, it's creating around this in a clockwise motion. I'm just going to call that a positive force. So that's going to be 2k times 5 feet. And then the next one I'm going to get to is going to be this 4k, and that's going the opposite way. So I'm going to call that a minus force. So that's going to be 4k times, again, 5 feet. And then the next force we have is this uniform load, and that uniform load at 200 pounds per foot per square foot is that we could deal with it as a uniform load, but life is going to be just much, much easier if we translate that into a single point load. So that 200 pounds per square foot is going to be, in terms of the linear foot of this beam, is going to be 10 times that 200. So we get a 2,000 pound load. But that 2,000 pound load, everything else we're doing is in Ks, in kips. So we're actually going to switch that. Kips is 1,000 pounds, so that's going to become 2K. So then we have another one that again is going in the negative direction, going counterclockwise. And so we have 2 kip times, in this case is going to be 5 feet plus 5 feet plus the middle of this 10 foot, so another 5. So that's going to be 15 feet. And then the last force we have to deal with is then the R1. And so the R1 is going in, again, presumably the positive direction. So I'm going to say plus R1, and its distance is going to be 20 feet away. Getting a little close to the edge there. So if we start to kind of do some quick things, that we're going to subtract R1 times 20 to both sides. So we get minus R1 times 20 is 20 feet is equal to 10 kip feet minus 20 kip feet minus 30 kip feet. So that becomes minus R1 times 20, which is equal to minus 40 kip feet. Since they're both minus, we can make them both positives. So now it's plus on both sides. So R1 times 20 is equal to 40 kip feet. Therefore, the R1 is equal to 2 kips. We've divided it by 20 feet, so that gets rid of the feet on the kip feet. So we have R1 is equal to 2 kips. So that means this reaction force here is 2 kips. Obviously, we just do a quick sum of the reactions. We can also, using the vertical forces, we can say if there's 2 kips coming down as part of this uniform load, plus the 4 kips coming down in this point load, and then another 2 kips over here, that's going to total to 8 kips. And we happen to know that this R1, because we've just figured it out, is 2 kips going back up. That means the R2 must be 6 kips. So there you are, sort of a long way around. It's actually pretty fast once you start to do it quickly on your own. You don't have to necessarily try to line everything up. And that is a pretty likely kind of question. You won't get a huge number of these, but you'll probably get one or two that sort of force you to kind of do some fairly simple statics just to kind of show that you can manipulate these things quickly and easily. Okay, let's jump on from there. So here's another type of question that they'll sometimes do. Check all that apply about slump tests. Slump tests, not sump, slump tests. Okay, shows the strength of the concrete at 28 days, shows the admixtures in the mix, shows the workability of the concrete, shows the amount of camber in a concrete beam, shows the strength of the concrete, shows the bearing capacity below the footing, gives an indication of the final finish of the concrete. So there's a couple of these that are actually the right answers, and then there's a couple that are sort of vaguely close that you could kind of get fooled by. But in general, there are two very clearly correct answers in this. So I'm going to jump ahead here a little bit. So those two correct answers are going to be that it's going to show the workability of the concrete, and it's going to show the strength of the concrete. A couple of the other ones that you might start to think would be shows the admixtures in the concrete. And the reason that you would think that is that there's a very strong relationship between a number of the admixtures. Admixtures are those things, those like chemicals and fly ash and a whole bunch of other things that get added into a typical concrete mix. And they have a purpose. They have some sort of need that they're doing. So they might make the concrete reduce heat when it's going through its heat of hydration, which is the chemical bonding process between the water and the cement, Portland cement. Or it might make the concrete more workable, make it easier to fit around the formwork. Or it might be a pigment of some kind. So there's a whole series of different types of admixtures that can be added in. And a number of them work on making it more workable. But the basic way that we manage the sort of workability is the water to cement ratio. And the less water I have, the stiffer the concrete is going to be. The more water I have, the more it's going to be like a soup, right? So this water to cement ratio is kind of the stiff versus soup ratio, if you will. And if I'm on a situation on a site and I'm trying to get the concrete to be placed very easily around a lot of different formwork and rebar and all the things, as a worker, I'm going to want it to be soupy. I'm going to want it to be able to get easily around all of those things without having to leave air gaps and pockets in various locations. But if I'm the engineer, I'm going to be very nervous about making it so soupy because there's a huge relationship between extra water and making it weak. The more water we have that is in there, it just creates openings and potential for cracks and a whole series of different reasons why it actually makes it weaker. So what I really want is just the exact right amount of water to cement to make the ratio, make it work as a concrete, to make it nice and durable and strong. But as a worker, I need it to be soupy so that I can get it to move. And so that's the thing that the slump test does. The slump test is this little device, which is this sort of cone shape that's shown up here. And you fill that cone upside down with concrete, and you turn it in this way, sort of fling it onto the table, you pull the cone back off, and you get this sort of lump of concrete left. And the amount that it slumps down is its slump, and that's allowing us to say that this is a stiff or a not stiff. You might have a slump of 0, at which point it'd be very hard to get it to fit around the rebar. You might have a slump of, say, 8, which means it's essentially soup and it's not going to be useful at all. It's not going to be strong at all. So usually you're looking for a slump of about 3, sometimes 2, sometimes 4. Kind of in that slumps a little bit, allows you to make it workable. So this idea of showing the workability is absolutely the point of the slump test. So you're sort of seeing the workability, but you're also seeing it in relationship to the strength. Some of these other ones, the concrete shows the strength of concrete at 28 days. That's actually something that you do with a cylinder test, which would be this one, where they make a bunch of cylinders. They're about a foot tall, about 6 inches in diameter, and you just make them out of every truck batch that comes to the site, and then you smash them at various points. And the typical one you would do is at 28 days because that's when it's sort of assumed that concrete is at essentially its sort of long-term strength capacity. Earlier than that, it's still green, and so it's not quite as strong. So you do it at 28 days, but that's for a cylinder test, and that's a very different thing. It doesn't have anything to do with workability. It's really just the end result of the concrete that came. As I said, the admixtures, it's sort of a possible answer. It's just that with the way that it's worded here, it doesn't give us that sense. It's really too hard to know what admixtures would be in the mix. So the only two that really make sense are workability and strength. Camber in a beam is when you have a beam that's built with a specific crown upward so that when it gets loaded down, that load will get it to essentially be flat by the time it's loaded. That's that idea of camber. And slump doesn't really have anything to do with the bearing capacity of the footing, and it doesn't really affect, it sort of affects the finish of the concrete in that you see more cracking and some of those things, but it wouldn't be a seminal part of the slump. That wouldn't be why you would use a slump to test in the field. All right, let's go to number 3.
So far, our guest answers here are tracking.
Cool.
So we have lots of correct answers so far.
All right. So number 3, I would use a mat or raft foundation when I expect there to be, and the answer to this one is, there's a couple different ways you could answer it, but the one that I was imagining is differential settlement.
Right too.
So what that's referring to is in a situation where if either I just can't be 100% sure about the soils that are around me, or there's really good soils, but they're way down and it's just not worth it to go down and find those really good soils. There's this possibility. What I do instead is I make a huge, big, thick raft of concrete. So this might be, 24 inches thick. It could even be thicker than that. It's probably not less than about 18 inches if you're going to call it a raft. So I have this very big, thick chunk of concrete. It's very, very heavy, but it's also loaded with rebar going in both directions. And the whole point of this is, if you imagine, this is sort of an odd drawing here, but imagine we're looking up underneath the raft. And let's say there's sort of a bad zone, here, which is sort of corresponding to this soil. Like it's kind of lousy soil there. And there's another bad zone there, and maybe there's another bad zone there. If those areas are just slightly less, have less capacity in their soil, well, it doesn't really matter because I'm getting the bearing capacity out of all these other zones of the raft. And so those other zones of the raft will just bridge across. The raft just becomes a beam across those bad sections of soil. So you're essentially making the entire slab a thick beam that spans across any of the bad soils that you're not even sure where they're going to be. So this sort of odd, you dig down and you're just not sure about it or whatever, then you put this big thing in, and then you're going to put all your foundations and everything else right on top of that. And it's going to spread the load, and that way you're spreading the load very, very wide. Every aspect of the floor is actually part of the foundation. It's not just where the strip footings are, the whole thing. And because you're spreading it all out, you can sit on some pretty crappy soils that way. One of the things that often comes into play here is if I have many feet down bedrock or something that's way down there, there's always this kind of a decision between, am I going to do a caisson foundation that's going to reach all the way down to that bedrock, or is it better off doing one of these rafts? And it would be a cost foundation, like the Caissons are very expensive. You have to go down deep usually with those. So if you're reaching down 60, 70, 80 feet, is it worth doing that to get to the bedrock, or is it worth doing one of these big rafts? They're very expensive to do, the rafts, and they're hard to manipulate in with plumbing and other things. It just creates a more complicated set of relationships than the typical. So the contractors don't generally like to do them very much. But in the situation, if I'm going to float a raft at 5 feet below grade, or I'm going to have to reach 110 feet down for caisson, I'm probably going to prefer to float the raft. So that's what this is all about. When you see that term mat or raft, that's what they're talking about. And this is one of those interesting examples. I'll mention a couple of these along the way. You actually don't see these all that often. I've done a couple. People I've worked with have done a few. So they show up every once in a while. And in certain kinds of soil conditions in certain parts of the country, they show up more often than others. But this is more of a thing that it's kind of an easy question to ask, if you will. It's like it's a concept that is sort of kind of by itself out there. It's sort of this way of imagining it, and it forces you to think about not only loads, but soils and the concrete and the rebar and a bunch of things all at once, and this idea of the relationship between making a decision between a cheaper version floating up high, closer to grade, a more expensive version of going all the way down to bedrock. So this is one of those things where they ask these kinds of questions about mat and rafts way more often than would make sense for the amount of times that it happens out in the world. And we'll see a couple of other examples of that as we go along. All right, here's another simple one. This one is very simple, but has a potential little trick in it that is obvious once you see it, but throws people off all the time, and so it's kind of worth running through it. So, okay, here, number 4, we have a 3-story building with no basement, slab on grade, has a column spacing of 30 by 30, and an assumed live load of 80 PSF for the floor and 30 PSF for the roof. If the dead load for both floor and roof is 20 PSF and the footing below one of the internal columns is 5 by 5, what is the bearing capacity? Like, what do we need to have in the soil? What bearing capacity do we need to have in that soil in order to make this be a safe building? And like a lot of these kinds of questions, you'll see it'll say ignore the lateral loads or ignore other things. And this is sort of their modus operandi. Like, what they want to do is they want you to sort of strip away all the side kind of thinking that you would normally be putting into something like this, and just focus on 1 or 2 small issues, just to make sure that you're capturing kind of what's going on in that sense. So here we have a little framing plan, and so we have a column spacing, we have the 30 by 30s, so there's the 30 and there's the 30, and here's the internal column, so the attributable area that's going to go to that column footing is going to be halfway between that 30 span, halfway between this 30 span, and then halfway that 30 span, and again the other side. So you're going to get a 30 by 30 in there. That's sort of obvious, but it's worth mentioning because sometimes you'll see a question like this and it seems very simple and straightforward in that same way, but then when you actually look at the way it's framed, one of these numbers will be different. So kind of the point of saying this is make sure you actually look at when they give you a framing plan, look at the framing plan, and you'll find that every once in a while it'll be set up in a way where it's not quite as simple. But generally it'll be, if you have a 30 by 30 column spacing, then the attributable area will be that same 30 by 30. So then we start looking at the loads. We mentioned that the roof load has a live load, a live load of 30 plus a dead load of 20. So therefore, that's going to be equal to 50. The floor loads have a live load of 80 plus a dead load of 20. So that's going to be equal to 100. I've obviously used numbers that add up to easy ones to calculate. 80 is not necessarily a typical number. It's not a bad number for a live load, but often it would be 100. For certain residential things, you might see it all the way down to 40 or 50. But 100 would probably be a little more typical for commercial. But this gives you just sort of an easy way to calculate. So for the roof loads, we're going to use 50. For the floor loads, we're going to use 100. So we start talking about the roof load. We've got 30 by 30. So that's going to be the area, and that's going to be times that 50. Excuse me, 50 pounds per foot. So we got pounds. Sorry, it's hard to do this with this little device. Pounds per foot. I'm probably not going to do that on the other ones because it keeps clicking me out. And you multiply that out, and that gives us 45,000 pounds. And then on the third floor, we have the same 30 by 30, and then we're going to multiply that times the 100 pounds per foot, and that's going to give us 90,000. And then on the second floor, you see where this is going. It's going to give us another 90,000. And then on the first floor, nothing. This is the little trick part that often throws people off. Because this is a slab-on-grade building, there is no structure at the first floor. There is no beam and column and all of that is being held up. The first floor is bearing directly onto the soil. So technically, if you want to be really technical about it, that 5 by 5 footing would actually have a little bit more load coming down directly from the floor directly above it. But in the way that the exam would think about it, it would just say, we're neglecting that, we're just going to simplify. So part of the thing here is that you understand that there's a difference between slab on grade and the structure up above. And of course, everybody would understand that as a difference, but you get sort of caught up in sort of adding the floors together, and often people will make that mistake. So we add those together, and we just get 225, I believe. And that's our total pound load coming down based on these code requirements of the 80 and the 20 and the 30 and the 20. And then we have the 5 by 5 footing underneath that internal column. And so that 5 by 5 footing is 25 square feet. So we divide that by the 25 square feet, and that's going to equal right there at 9,000 PSF. And so that is what the soil capacity is going to have to be in order to have this work. So I have to give you a little heads up here. When I actually did this, I actually wrote this as 6 by 6, but for some reason I had a little typo, and I made it 5 by 5. So that's why I've just left it at 5 by 5, because I didn't want to send a change out and make it more complicated. And it works at D. So in this case, D is the answer. But if it was 6 by 6, which would be more typical, because 9,000 is actually quite a lot of PSF. And for it to be 9,000, that would really be saying that it's probably bedrock of some kind, some sort of rock. If you do it at 6 by 6, it comes out to about 6,000, which puts it in 7,000, which you can get 7,000 from a couple of different soil sources. So that's why it seems a little odd. It's because I actually had meant it to be 6 by 6. But it still works at 5 by 5 in terms of going through the process. So you'll find the sort of soil capacity loads, they'll range between, probably the smallest load you'll ever find on the exam would be something like maybe 1,000 or 1,500 PSF. That would be pretty not great soil and would only be really usable either in like the mat or raft like we just talked about, or in something of a fairly small scale type structure. Anything that was a bigger scale structure almost assuredly would be at least 2,000 PSF and probably 3 or even 4 or 5,000 PSF for what you'd be looking for in that soil. And if you didn't have it at a place that was easy to get to, then that's going to mean that you're probably going to reach down farther into that soil until you find it. That's why you're going to use those soil boring reports in order to figure out how far down that foundation would actually go in order to get a reasonable pounds per square foot capacity of the soil to be able to push back so that the building doesn't sink into the ground. So again, fairly simple idea, just has that one little trick on it that you have to remember, that slab on grade has a different relationship to these numbers. Another framing plan concept here. So when choosing a framing plan, number 5 here, for a steel structure, the engineer offers 4 different potential layouts. Since you are concerned about efficiency and economical use of material, which would you choose? Assume it's an office and sort of typical corrugated steel decking. So let's look at B and D first. So we look down here at B and we have a 60-foot dimension here and then 40-foot dimension there. So we've got beams at 60-foot spans and girders at 40-foot spans. Well, that would be really great. That would be awesome because there'd be no columns and it would be easy to put a building in around there. But it's not going to be economical and efficient. Typical sort of sweet spot of steel framing is going to be in the kind of 30-foot to 40-foot. Sometimes you'll see people say 35-foot to 45-foot. So you kind of get the idea. 35 to 40 is sort of that range of column spacing is going to work very efficiently with steel. As soon as I get down to like 20-foot spacing, there may be reasons why I do 20-foot. There's all kinds of reasons why we don't do things in the most efficient way. But when we get down to like 20-foot spacings, it's just a little less efficient. The amount of steel I need for the columns and all the footings that requires, it's just the numbers when you work them out make that less efficient. So that's one of the issues that's striking against D. Not enough columns in B, and probably too many columns, too close set together in D. The other issue is it's for an office occupancy, it would just be not great to have columns every 20 feet. It's hard to fit the offices in that scenario. The other issue with D is steel decking. We're imagining that there's steel decking spanning across from beam to beam, and the shortest dimension I have here is 20 feet. And steel decking, generally, you can make it span different dimensions, but generally, especially in terms of the exam, it's going to be in probably the 6 to 10 foot range. Might be up to 12 or even 15 feet in certain scenarios. It might be down to 3 or 4 feet spacing in other scenarios. But it's kind of, again, the sweet spot is going to be around 6 to 10, maybe 12 feet. And so it would be very expensive corrugated decking that would span 20 full feet in this whole dimension. So B and D are not right. So then the question is, all right, which is it between A and C? And the trick on this is A and C are very similar, except switched, sort of polar opposites, if you will, of each other. So we look at C. I have beams here spanning from girder to girder, and then I have girder there and a girder there. So if you think about each beam loading, the area for each beam that it's carrying is roughly something like that, and the area for each girder it's carrying is actually pretty darn massive, right? Because I have short beams and I have long girders. So what that's going to mean is I'm going to have a girder that's going to be very, very deep, and then a beam that's coming into it that's going to be a little tiny beam that comes into it. There's going to be a big discrepancy between those two. And it's going to be a very expensive girder system. You're putting huge amounts of money into the girders, but also you're making it more difficult, less economical for moving ductwork around the building, for having space for all those other elements that you want to have up in the interstitial space. And so it's just considered a not smart way to go. The exam will always lean towards, unless it gives you a reason to go against this, it will always lean towards the idea of having a nice long beam and a short girder. so that way the depth of those steel members, those presumably wide flanges, end up sort of equalizing. So you'll end up having a situation where I've got my girder and my beam coming into it is probably pretty close to that same depth. That's going to be more efficient for all the interstitial stuff like the ductwork, but it's also going to be more efficient in just straight out weight of the steel and the sort of economy of the process. And so this is allowing us to get sort of the best of both worlds as best as we can out of the 4 choices that we've got. Hopefully that makes sense. And then the spanning of the decking on that is kind of below 10, so easily works in the typical steel decking spanning. All right, let's look at number 6. So for design reasons, you do not want to use shear walls in the building because you need larger windows than the shear wall could easily accommodate. So instead, you would probably employ, and we have a couple different answers, massively hinged columns, braced frames, moment-resisting frames, Vierendeel frames. So looking at kind of a diagram of a sort of 3D frame happening here, the typical, you would have shear walls, and those shear walls would be put in sort of logical locations. And the reason for that is if we don't have any shear walls in that big mix of framing members, and we get one of these forces pushing against it, there's no diagonal forces, so it just pushes it over. It goes from being a square to being a rhombus, right? It makes it a parallelogram. And so if you had a force against one of these side walls, wind force or shaking force of some kind, it would just sort of knock this thing over. So the typical way that this gets done is you end up building these shear walls in very specific locations, which are big solid mass of walls, often concrete or block, reinforced block, or something along those lines. And I would have I wouldn't just put one in, I would probably try to balance it so that the shear going in that direction, as the wind is coming up this way, it's stopping this force from knocking this thing over. I don't need to have it everywhere, I just need to have enough there that the rest of the frame can just sort of lean against that, and it's going to keep it stiff. I'm also probably going to want to have it be balanced in the floor plan, so that I don't have a torsion starting to happen where it's stiffer on one side of the building than it is on the other. So if I have this one, I probably have another one on this other side. But equally, I also need to worry about going this way. So I'd probably have another shear going the opposite direction in order to stiffen the building in that way. And again, I would try to do it in a balanced way, so I have equal, kind of around the center of gravity of the structure. It's sort of even and symmetrical. And if I have that situation, so let's say I've got them here as well, like I said, for kind of some symmetry purposes, well, clearly that's going to make it really hard to put a window right into that spot. Now, I can put a window into a shear wall, I just can't put a big window into a shear wall. So the question is, all right, what if I, for design reasons, really want to have those big windows? What are my various choices? So the shear wall kind of is out because we just said we can't fit great big windows in there easily. So what are my other choices? Well, I could use what's referred to as a braced frame. So I could use that. That's actually a pretty good answer. And in that situation, I might be thinking of big diagonals. It could be like that. It could be, oops. Well, sorry, you want to get rid of it? Okay, one more. All right, there we go. Or it could be that you do them as smaller ones that all stack up. And I would do that in a few of the bays. And those braced frames are actually pretty useful, and they can do all kinds of great things. You might be thinking of the Hancock Building in Chicago, or maybe you might be thinking of the Pompidou Center in Paris. The Pompidou Center in Paris, because they were trying to show up, really make it sort of show all the structure, they actually have those braced frames in every bay. And that's actually not necessary. You only need it in probably about 20% of the bays, roughly. But they did it all over the place just for the sort of fun of it. But you only really need it in some. But if we're really kind of being serious about putting big windows in, this is also kind of problematic, right? I can't really easily fit a big window with that big diagonal steel member running through that space. So yeah, it sort of answers the thing, but it specifically talks about big windows. And while I don't have any problem personally with having a window with structural members going by, it's kind of a fun thing to do. That's not really what it's talking about. That's too designy for this kind of conversation. So then, all right, how do we do it without putting that in there? And then the obvious answer here is with moment-resisting frames. So what that's saying is, instead of all of these points, like this point right there, being considered a hinge point, instead of that kind of connection, very simple bolted connection that can actually provide quite a bit of movement in there, a moment resisting frame is saying, I'm essentially welding all of these connections, and I'm making those connections so that they are not hinging, they are not turning, and it's making the actual frame, that's the thing, those connections where the beams and columns and girders all come together is what's going to stop this force from pushing that frame over. And it's going to do it in such a way that I can still get a great big window right in that spot. So that kind of frame is the moment-resisting frame is definitely the sort of answer that they would be looking for. Typically, that would be a welded frame, though you can actually do it by bolts, but when you get into the details of how you do it with bolts, it takes a whole lot of bolts. And so it's actually usually easier just to weld it, because it's hard to fit all those bolts in there, because you're trying to make a very, very stiff connection so that it just can't sort of tilt over in that same way. Massively hinged is just something I made up, so that's definitely not it. The answer would be moment resisting. And Vierendeel, this is one of my favorite words that shows up on the exam occasionally, and so I bring it up a lot because it's something that you probably haven't dealt with. A Vierendeel is a truss type, and it's a fake truss type. It's a truss that uses moment resisting frames. So it's, instead of having any diagonals in it, it just uses those same moment frames at all those points, and therefore it's kind of acts like a bridge truss, but it's not, it's called a truss, but it's not actually a truss because it doesn't have the diagonal forces in it, but it has this weird name. And again, that's one of those things, there's certain words that show up over and over again because they're sort of they're a known thing, like a mat foundation, a Vierendeel truss, a whole bunch of those kinds of ideas. And so when you see those in guidebooks or in these kinds of lectures, make sure you sort of catch on to those, because there are reasons that people are talking about those, and that's because they get used a lot in these kinds of discussions. All right, on to number 7. All right, we're stepping back to some of the statics discussions here. Draw the shear and moment diagram for the beam shown. So the beam shown is over here. I've got 2 reactions, reaction 1, reaction 2. I've got a uniform load across the entire beam. I've got a singular load, a point load coming down there, that's 7 kips. I've got some numbers on here, but I actually don't really care about the numbers. You don't really need the numbers to be able to draw the shear and moment diagrams. Before we jump into doing it, I'm going to break these out into 2 separate elements here. So here's an example of just a typical beam with 1 single point load on it. When we do the shear diagram, what that's going to be, we have this load going up, and then that load going down, and then the other load going back up again. So from a shear standpoint, that's That's going to get us that flat line across, that big drop down, the flat line across, and then back up to 0. And remember, it's always got to get back to 0 if it's in equilibrium. So then comes the moment diagram. And there's a bunch of different ways that you can think about this. For me, when you're talking about diagrams, I actually prefer to think of it graphically. So the way that I think about it, like I say, there's about 3 different ways to do this, but the way that I think about it is that the value that's on the shear diagram at a given point, so let's say a few feet off here, let's say we're talking about a point right through there, so a point a few feet off that edge. The value that this diagram is expressing of the shear diagram is going to tell you the slope of the moment diagram. So the value is going to tell you the slope of the moment diagram. Well, you notice here on this shear diagram that that's a flat line going across both at the upper and the lower level. So that flat line means that the value of the shear diagram is a consistent even number in these 2 different scenarios, which means that the slope is going to be a consistent slope in those 2. So when I have a point load like this, it leads to a sort of boxy looking shear diagram, which leads to a little peaked roof of a moment diagram. If I have a uniform load, then what I have is I have that reaction going up, and then I have a consistent load going down. So I have a little bit down, right? And so that's going to mean that I am going to end up with that diagonal line as it goes down, and then it comes back up to cut back to that 0. So I get these triangular shapes when I have a uniform load like this. Well, like we said, if we take at any given point the value of the shear diagram, the value at that point of the shear diagram, it's going to tell you the slope at that point of the shear diagram. So here, in this location right there, we have a fairly small value, but it's a positive value. So we know it's going upward. Here, at the very edge, we have a larger value, and it's also positive, so we know it's steeper. So this is going steeply up and then eventually nodding off to 0, because at the 0 point it's going to be flat across, and then now it's, because it's on the negative side of that line, it's going to be going back down in the same format. So if I have a uniform load, I've got triangles and then curves. If I have a point load, I've got rectilinear boxes and then these angle lines for the moment diagrams. So, okay, we come over to here, and what does that mean for our actual drawing of an actual shear diagram? And we're going to end up doing something like going up, sloping down, a big drop, continuing the slope. That's probably not quite steep enough, and then back up. So that's going to be our shear diagram. So we have a positive value that starts higher and gets lower to eventually where that point goes. And then we have a negative value that starts sort of as a low slope and becomes a bigger slope. So that's going to do, we know there's an important thing happening right through there. So it's going to be something like, doesn't go to flat, it's still angling up. And this one is also doesn't go to 0, so it's going to be still angling down. This one's going to be a little tricky here. Sorry, that's supposed to, I'm going to cut it there. That's supposed to be an arc, but it's still sloping upwards by the time it gets there. So that's how this is going to work. You very quickly just map out how the loads are loading, what the shear diagram is going to do, and from that graphically you can just visually see what the shape is going to be. I know it's going to be curved because of that uniform load. These would meet each other. Sorry, it's a little hard to make it do that, but those would actually connect at that spot, then it'll find its way in negative. It's sort of starting off low slope and then steepening up as it gets down to the end side. One of the things to remember about this is these things are totally just fictions of our imaginations. These are structural engineers, how they think about numbers, and there is nothing sacred about any of this. We just happen to be looking at it from one side. We could look at it from the other side. We could decide that the reactions go down instead of up. We could decide, these are just ways of thinking about it that help us to see things like where the moment is the highest, where the moment is zero, where the shear is the highest. It's just a tool by which we use. There's nothing sacred about these things. They're just diagrams, and you can flip them around and use them in all kinds of different ways. So I've shown beams because beams, I think, are easier for people to understand, but you can have very similar things on walls, on columns, on purlins, on any number of different pieces. And it's that same basic idea that you're just diagramming how the forces are working in order to be able to make decisions from what you would need to know. Like, can I put a hole in the beam in this location? Does it make sense? Or is something else, does it need to be more robust at that spot? So this is the kind of tools that get shown. You won't have to do a bunch of these, but you won't actually draw them, you'll choose them typically. Although under 5.0 you may have to draw them. But you will have to choose among them, and if you can see that fact that the point loads give you the boxy shear diagram and then the angled moment diagram, and that the uniform loads give you the triangle shear load diagram and then the curving moment diagram. Once you see that and you understand that sort of slope is related to the amount of the shear diagram, the slope of the moment diagram is related to the amount on the shear diagram at that point. Once you sort of have that in your head, it's actually really easy to pick out the correct answers. All right, let's jump on. Number 8. So with this, we're talking about an earthquake situation. And this is actually a take on one of the NCARB questions. So you may feel like you've seen it, and that was actually sort of purposeful because it's a bit of a trick. So the actual one in the NCARB piece looks like this and has the same arrows. And in that question on the NCARB mock exam, the point that you are most worried about, so the question is, in the elevation of a multi-story building subject to earthquake forces, this elevation that's shown, which location is likely to be the biggest problem? So on the NCARB version of it, that spot right there, so the C one would be the correct answer. And the reason for this is, once you start thinking about it, it totally makes sense, right? If I have an earthquake, what's it doing? It's shaking this building up, so it's shaking this thing back and forth. Well, that taller element is going to shake in a different pattern than this big block at the bottom. This is still going to shake, but it's going to be much less of a shake than this bigger, taller piece, which is going to start to have these, much bigger. That's probably a little dramatic, but it's going to have these much bigger sort of motions. Well, where's all the action happening? It's happening right at that inner corner, that re-entered corner. And so it's flowing one way to the one side, and then it's flowing the other way to the other side, and there's a huge set of forces happening right in that spot. But that's not what I drew. What I drew was this one with these very tall columns. You can see these are at least a double height story here compared to these other floors. And this big, tall space with just these columns. Now, maybe there's very stiff shear walls back farther in or something, but it's sort of clear that the way that's drawn is that this is meant to say this is a thing that's happening on this elevation. There's something going on here. And what that is it's an irregular massing. It means that I have a very heavy mass up above, And not only that, but an irregular heavy mass up above, so it's going to have lots of different movement going on. And then I have this very light, because it's just open columns, very light mass down at this bottom area. Lots and lots and lots of famous earthquake failed buildings are failed because of this. So the answer is actually A, because what happens is this big block, imagine if you have this thing, imagine it's a brick sitting on a bunch of pencils that you've stuck into the ground. And then you start pushing the brick back and forth. You know, the brick isn't going to fall apart. It's the pencils that are going to start to wobble and fall over. And so this area can very easily find that these columns start to get squinched and it just all comes crashing down. So A is a huge, big problem. C would be the next problem and is probably actually also a correct answer. But in my mind, I think A is a more correct answer, which is one of those things that the exam does quite often. So you might think about, well, what could we do about this? Well, for one, we don't do a light first floor like that, or even up in the middle space. Keep it all consistent as much as you can when you're in an earthquake zone. And instead of having like this original one, this sort of kind of elevation L, what if we did it where we had a tall building and we did a separate, sorry, a little off there. And we made these two separate buildings just from a structural standpoint, but still made it so you could walk back and forth between them, right? Then this building is going to, move at its pace. This building is going to move at its pace, and everything's great, right? So this is sort of one of those examples where if you saw a couple of different versions, there are things that, maybe it's not that you can't do this building, you just have to find a way to do this building. What do you think the issue is if you did it this way? Because this has its own problems, right? The issue on this one is this thing is rocking back and forth at a different amount and a different pace than this lower structure is. And so the issue here is, do I get a spot right there where they're pounding each other, where one is literally banging into the other, and I get a problem point there. So I would have to make sure that the amount of distance that it was going to be swinging as it went through its various motions set up by the earthquake would be within that distance so that it structurally wasn't damaging itself in that process. It's sort of assumed that in an earthquake you're going to have some damage. Like the point is not to have zero damage. The point is to have as little as possible structural damage so that it's actually the buildings are staying up and keeping people alive inside them, and you're not having a huge amount of damage of decorative elements that can cause other kinds of like big things falling on people or something like that. So it's okay that these things might bump into each other as long as what they are going to break is something that's not going to be a major structural aspect. So you can figure out how much space in between you would need just by understanding the amplitude of the movement. Okay. So number 9, after bringing in fill from an outside source prior to the foundation installation, what test would be appropriate? So we have the vane shear test, we have the Proctor test, the cylinder test, and slump test. Well, we've already talked about the slump and cylinder test. These are concrete tests, so it's definitely not either of those, and that's these guys down here. There's the slump and the cylinders. The vane shear test is kind of an interesting one. It's related to these issues, but not in the way that this question actually asked about. So the vane shear test is I have a stick, it's more complicated than that, but I'm going to call it a stick, and it's got this sort of little cruciform shape down on the bottom, and I stick that thing down into the ground, and then I turn it. I try to spin it around. And if it spins very easily, that means there's very little lateral shear capacity in that soil. Well, that would be useful to know if you're using the soil as part of a way to stop the building from sliding or the retaining wall from sliding or something along those lines. There's a lot of different elements that would be important to know, but that's not what it was asking. What it was asking was, after bringing in fill from outside source prior to the foundation installation, what would be appropriate? The main thing we're talking about here is actually its compaction level and its ability to sort of withstand a load. So the Proctor test is this interesting thing where a realization got made that there's a strong relationship between the moisture content of the soil and the ability for it to be compacted. And so the Proctor test allows that to be sort of figured out, that you can it's a very simple test that tests with a series of blows and tries, but understands how much moisture is in that soil. And they do a whole bunch of them from that particular kind of soil, and then they find the sort of the kind of best example. And then you get a readout that gives you a peak compaction capacity, and then when you're in the field, you're sort of aiming for about 95% of that. So you'll often hear people talk about it's 90% Proctor test, which means it's not quite compacted enough, or it's 97% Proctor, which means we've compacted even more than we really needed to, because 95%, you're so close to 100 that there's enough going on in the soils. It's not like you're ever going to be perfect in the soil. There's factors of safety built in all sorts of other ways. So Proctor test is this thing that's figuring out about the compaction. It's related to the moisture content, but you're looking for what the peak compaction capacity is, because you want to get it compacted so that nothing moves later. And in the field, you'll usually find that you're aiming for 95% of that peak. It's one of those terms that you'll see a lot. Okay, number 10 here. What this is asking is the top chord of this cantilever frame in tension or in compression? Just visually, we can probably tell that it's in tension, right? Because I have a fairly heavy load coming down here at that outside point, and have a relatively light load comparatively to that heavy load pushing back in the other direction. So I'm pretty sure this thing is going to be stretching out like that as it gets loaded. So I'm pretty sure it's in tension. But just to check it, I can very easily do a moment around this location. And what that does is it allows me to get rid of this sort of more complicated load there on that angle, as well as getting rid of any of the loads that are happening in this wall this way, because again, those are loads that are going at a zero distance. And so the moment, calculating the moments across the whole thing, that set of moments are all going to get crossed off because they're all zero distance away. So the only two loads that I have left are the 2K, the 5K, and then a response up here that's going in one of those two directions. So if we actually did the sum of the moments, it's a fairly simple calculation. I probably won't bother going through it, but it would be a 10-foot dimension times the 2 kip, a 10-foot dimension times the 5 kip. One of those is going this way, the 2 kip is going this way, the 5 kip is going this way, so those are going against each other. And then the question is, which way is this other one going? And I'm going to assume that it's also going in that direction because I think it's probably in tension. And if we do quickly kind of calculate it out, you'd find that, in fact, yes, that is, I think it's a 3 kip load at that point, although I'm not 100% sure about that if you get the calculation. But it's definitely in tension, and you can do it very simply by choosing where that moment wants to get taken, so you can get rid of all the complicated parts. Another way to do it is by a force diagram. So you might start at a starting point, go 2 kips over, 5 kips down, the angle, which is whatever it is, because it's just a diagram, so we know that it's associated to the same length as these forces. And then to close it off, I have this coming back, and again, that's that force, and that's showing that it's going in the same direction and that it's in tension. Okay, let's move on to the next and last one. So this is one that comes straight out of the NCARB, the current NCARB exam. I usually only do 10 for this, but when I was kind of glancing at it, I thought, oh, this is kind of a nice one. We'll just do it as a quick little bonus thing, because it, I think, gets at a couple of useful concepts. So this question is, buckling of a column can be reduced by which of the following? Check all that apply. So we look down through the possible answers, and we say, well, all right, increasing the size of the member. So the size of the member, that seems reasonable. Rotating the column, that sounds suspect to me. We'll come back to that one. Bracing the column, that's absolutely going to work. So I'm going to say increasing the size of the member, bracing the column, those are both good answers. Changing the type of end restraints, that's also probably going to be very helpful. Reducing the length of the column, well, that's going to be hugely helpful. Reducing the R, the radius of gyration, actually that one's sort of a little trick. It would actually, you would want to be increasing the R for that to be useful. So rotating the column, what's the problem with rotating the column? In order to understand the process here, like I have let's say a wide flange type column. It has one axis going this way and has another axis going this way. Well, clearly, this is the strong axis, right? That's why we have beams that look like this, because it's going to be very hard for that to bow underneath the weight. If we actually put the beams this way, they would be much easier for that to sag in comparison, right? Well, the same thing is going to be true in columns, that I'm going to have a weak direction of loading and a sort of more robust direction of loading. So in order to figure out whether this column is meaningful, I, at base root, have to do both directions. I have to test both directions, because I know I'm going to have to do the weak axis, because that's where it's more likely to fail. Right? It could buckle in the weak way just as easily as it can buckle in the stronger way, so I have to test for that. So rotating the column, the rotation is already taken up in how I'm actually doing my calculations. So that doesn't really answer us. Increasing the size of the member, that absolutely can make a big difference, because now I'm making that whole thing stiffer and heavier, and I'm making it deeper, and so that can be a very big advantage, but I would have to make it in both axes for that to be meaningful. Bracing the column, if I have this big long column and it's braced at, say, the halfway point in one direction, if I can be clever about it and have it be braced so that the weak axis is braced and the strong axis goes the whole way, well, that's effectively making the overall length of the column in the calculations half of what the other one was. So that's a huge difference. So bracing makes a big difference. And then we think about the end constraints. You probably remember these diagrams. If I have this end constraint where this is a pin joint, then this thing can bow out all the way from one pin to the other. But if this is actually a fixed joint, then it's not going to be able to do that. It's going to stay in a 90-degree relationship for the first bit, and it's going to do something more like that. And that reduces the effective length of the column. And so what that's telling us is that the end constraints, the end restraints, make a big difference on what the capacity of this column is going to be in terms of its buckling. And remember that when you're talking about columns, you're always talking about, first, there are sort of three basic types of columns, right? I can have a very short and stubby column. I can have a medium column, and then I can have, I'll do it over here, some really long, slender, ridiculous column, right? And when I'm trying to figure out what calculations I need to do, it's very clear that that short, stubby column is not going to buckle, right? that's just never going to happen. It just can't. You think of it like a brick as a column. It's just not going to buckle. It might smash. So what you would be concerned about is the actual capacity of the material itself. That's where I would put all my energy in terms of a calculation. And then I look at this very tall, slender column, and there's no way that tall, slender column is going to get to the point where the material itself is smashing, right? It's totally going to buckle before you get to that spot. It's going to bow out because there'll be some little bit of lateral load somewhere, some eccentricity, and it's going to push that thing out, and that's how it's going to fail. So that one, I'm going to be all about looking at the modulus of elasticity and understanding its ability to bounce back, and looking at the buckling numbers, calculations. This middle zone is the one that's sort of annoying, which is actually where a lot of actual architectural projects are, because that one I can't be sure which situation it's going to be, so I have to actually do calculations for both of them. So I just like this one because it starts to talk about a lot of different issues. You'll see the KL over R, so the ratio that has to do with this issue of the way that it's restrained is the K, the L is the length, the R is the radius of gyration, right? That simple simple formula allows you to start judging where and what of these calculations you're going to need to actually do. And I think that brings us, we're a couple minutes after 7, sorry about that, but brings us to the end here.
All right, we do have 2 questions here. So Cipriano asks, going back to our first question, what type of soils would require the raft?
There's a couple different ways to answer that, and it's possible that it would be, say, like a silty sand or something that has a little bit of clay in it, that there's going to be a little bit of movement and a little bit of settlement changes as water table changes for whatever reason. And so the kind of lesser soils, and you're going to float right on top of them. The other issue, though, is that it's just a very differentiated, like sometimes you can go out onto a job site and you have a great big site and they'll do 5 or 10 different soil boring tests at different locations, and they'll all be exactly the same. And that, all right, this is going to be a very consistent set of soils. And then at other times when you go and the soils are actually ranging quite dramatically in different locations. It may have to do with previous rivers or dunes or underground rivers or all kinds of other factors can play into these things. And so there are times when you just don't know what you have. You have a pretty good idea, but you just can't be sure. So you might have actually pretty good soils, like good solid sands or gravels or something, and you're going to float on top of that, but you're just worried that somewhere in there's going to be this lesser soil. And so you want to be able to span across it. So the answer to that is it's going to be in those the soils that have the lower levels, but it's mostly about that kind of mixed soil scenario, and that often has to do with water table issues as well.
Okay, so the second question we have here is from Charisma. She asks, is there a formula to come to the area multiplied by the load? And I think this goes back to the second slide, maybe.
The area by the load. No, maybe.
Question 4, she clarified there.
Yeah.
There we go.
Yeah, there are a number of different formulas, so I'm actually going to not answer that one because I don't want to confuse you. There are a number of different formulas, but this one, what we were looking at here, was actually just a very simple, straightforward thing that I have a certain quantity of load coming essentially straight down. Now, in actuality, when we're really doing a real building, there's a bunch of other things going on. There's bracing happening, there's lateral loads happening, but in this kind of question, it's really just talking about that straight load coming straight down, and it's going to sit in that. So if we think of that load as a column sitting on a footing, and the footing has a size, then the whole question here is, can that entire load, that whole big load coming down, be held up by the soil that's down below it, right? So the question then is, well, what is the capacity of the soil? So if the soil is, say, 3,000 pounds per square foot, that means we can judge how many square feet we have times 3,000 pounds per square foot. And if that number is a bigger number than our total load, then we know that that 3,000 PSF soil can work. In this scenario, the way that we did it, those numbers, 3,000 wasn't anywhere near close, so it would have to be either a much bigger footing, or we'd have to go down to a better soil.
Okay, so that's, does anyone have any other questions? All right, so thank you, Mike, of course, and thanks to everybody who tuned in.
Thanks, Mark.
And for everyone who submitted their questions today. If you'd like to attend our next ARE live broadcast on newly licensed architects and how they pass the exam, visit blackspectacles.com/podcast to register, which is right here. It's what you're looking at.
That's going to be a really great conversation, I think. It's
Yeah,
always good to talk to people about kind of what worked for them. You see a real range of different ways of approaches. People using books, people using videos, people using, like, how did they focus? How did they get the work done? It's a really good one to check in on.
People who did it in 7 days, and people who did it in 7 years, and people who did it in 7 months, and 7 weeks. It's quite a range, of course, as you say. So, but at that, and it'll be nice. You'll be able to ask questions and share any answers with Mike for live feedback during the broadcast, as well as all the other attendees. So let's see here. If you also, I should also mention, if you want to learn more about our AIA ARE prep curriculum, you can visit blackspectacles.com, where you can try out any of the free video courses. And for those of you who are ready to start preparing for the ARE, and if you're already an AIA member, as a part of our partnership with the AIA, you can visit bksp.es/923webinar to get a 15% discount for the entire duration of your AIA ARE prep membership. Finally, please leave a comment below the video to let us know what you think and share any suggestions you may have. I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.